This is, some people call it the Chebyshev problem. Okay. And the third one in the list is this. See, here as well as in least square, whether I put a 1 by n here or not, it doesn't matter, right? Because that's a fixed constant. So if I put a 1 by n here, then it is not the sum of absolute deviation, it is going to be the average of absolute deviation that you minimize, okay? So this problem is equivalent to minimizing the average of absolute deviations. Or if you have the least square problem, then it is equivalent to minimizing the average of the squared deviations. So some people propose the following one. You minimize Cm, not the average, but the median of so they call it the least median of, they actually call least median of squares problem, but whether I put a square here or not, it really doesn't matter much, right? Because ordering of the absolute values and ordering of the squares, they are going to be same. So least median of square or least median of absolute deviation is the same thing, okay? So I have 3 problems now. This is, let's say this is problem number 1, this is problem number 2, and this is problem number 3. Interestingly, none of them will have a nice solution like the least square problem. And it took people a while before they could solve this. The first complete solution to this problem is due to Gauss. So when Gauss wrote his book on least squares, he actually discussed this problem also there and gave a complete solution. Okay. What is Gauss's solution? So I have n data points, and let's say that I have a situation where no 3 points are on the same line, to make things simple. Okay. All these x's are distinct, because they are like when, for example, when Legendre collected his data, Legendre didn't collect the data twice at the same place. Okay. Legendre collected meridian arc lengths at different places, so x's were all different. Okay. And also the points, no 3 points in that data will be on the same straight line, so that condition is satisfied. Okay. So Gauss showed that in that case, I can join any 2 points and I will get a straight line. So if I have n data points, how many straight lines I will get? How many? N minus 1. N choose 2. That is n into n minus 1 by 2. So many straight lines I will get, right? And Gauss proved that one of them is the optimal line. So this is Gauss's result. Okay. These lines are called elemental lines or candidate lines. So if you want to solve this problem, one way to solve this is that find the equation of all n choose 2 lines, check which one has the least absolute deviation, and that's your answer. Okay. Now there are better algorithms than that. In fact, what one can show is that this same problem can be formulated as a linear programming problem, and there is a more efficient solution for most of the data set that I will handle. Okay. But unfortunately, even the linear programming will not help you when your n is really, really large. Like if you have what we call today like a big data problem. Suppose we have the height and weight measurements on all Indians living today. So 1 billion people roughly. Okay? And we have, say, the height and weight measurement on them. And we want to fit the least absolute deviation line there. Okay? This is a problem you will have difficulty if you use the simplex algorithm to solve that. Okay? Because of the sheer size of the data. Even though there is only one variable, so it's not a high dimensional data, but the size of the data is so big. Okay? But we have this algorithm now. So what the algorithm is telling you that you have to find the right pair of points and the right elemental line, right? Because there is one elemental line and one pair that is optimal. We know that. So now how do you use simulated annealing? Tell me how you formulate the simulated annealing to solve this problem. So I am going to take two Indians at random, take their measurements, find the line, evaluate this thing for the entire data set. That will be a huge task already. But that will give me a value for the function that I am trying to minimize. Then I will choose randomly another pair. And then I will evaluate this thing. And I will decide whether to keep that one or not using my Metropolis Hastings algorithm. And run this few times. And hopefully, I will converge to the global minimum. So this is one way to do that when your n is very, very large. Otherwise, it's not worth. Because simplex will be way much faster than this. If you use simplex algorithm for reasonable n and p, a reasonable number of variables. By the way, this result is not only true for line. If you have the least absolute deviation problem with several variables, Gauss actually stated the result like this, that you can have a hyperplane passing through p of the data points that will be optimal. Okay, so this Gauss's result is more general than that, but I am just taking the problem line. Okay. What about this one and that one? This one actually doesn't have a nice characterization, but there is a link between this problem and this problem. See, if I have, okay, before I solve this problem, let me try to solve a simpler problem than this one so that you get the geometric idea. Do you understand why or how simulated annealing can be used to solve this problem? That's because of Gauss's result that one elemental line is the optimal, and finding a solution to the minimization problem is equivalent to finding one optimal line. That's equivalent to finding a pair of data points. And that pair you can generate by simulated annealing. Okay. So you start with one pair, evaluate this objective function with the sum of the absolute deviation, see what you are getting, and then you take randomly another pair, and then you decide using Metropolis Hastings which one to keep. Okay, so that's least absolute deviation problem. Now, what is the connection between this problem and that problem? Before that, before I show you the connection, let me show you a simpler problem. Suppose I don't have x and I have only this problem. What do you think will be a solution to this problem? Suppose I give you a bunch of y values, no x. I'm trying to find a constant so that median deviation from y is minimum. If I ask you, what if I have the average, then you know the answer. What is the minimizer? If I have the average, it is the middlemost value or the median. But what if I have instead of average the median here? Try to think about a set of points. So maybe you have 3, 4 values, try to draw a line and sort of plot those points and look at the picture and think about it. Say I have 5, 10 points, say 10 points and 10 values, and I'm trying to find the value c such that if I look at the deviation of each value from c, the median deviation is least. Anybody has any idea? So if I draw a picture, say the y values are like this. These are the different y values. Like that. What should be my c? Yes? Anybody knows the answer to this question? It's a good exercise actually. Sometimes in elementary statistics textbooks it is given. I mean, if you have seen it, then you should know the answer. Okay, so let me tell you the answer, then you'll probably get that, okay? So what you have to do here, you have to look for an interval that covers half of the data points. Okay? So you have to look for an interval. Suppose I have 10 data points here. You have to look for an interval that covers 50% of the data points. That means 5 of the data points. Now there are several such intervals, right? So one interval here, if I shift it and add another point, I'll get another interval like that, okay? Now, the interval that has the shortest length among these, the midpoint of that is the solution to that. Okay? It's very easy to check that. Okay? So once you know the solution, it's like, when you have to find out the solution, it might be a very difficult problem. But if I tell you the solution, proving that it is the solution is not so difficult. Okay? So what you have to do is you have to look for an interval of the shortest length that covers 50% of the data point, and the midpoint of that is the solution. Now, when I have the linear equation there, what is the natural analog of that? So it's like if I draw a picture, so these are the points. And I'm trying to find a line so that if I look at the median of these deviations, so there are different deviations for different points. So I calculate the median of these deviations, and I have to choose my line in such a way that the median deviation is the least. So if you follow the analogy from there, what do you need? So here I was looking for an interval that covers half of the data point, and I had to find the shortest interval. So in particular, suppose your data is coming from a Gaussian distribution. What will this lead to? So you have the peak of the Gaussian distribution. So where should be the interval of shortest length containing 50% probability? It's at the center, right? So this is between the first quartile and the third quartile, right? So that is the interval, and the midpoint of that is the median. So that is what is going to be C. So that is for a symmetric distribution like Gaussian. Okay? If the data is not so symmetric, then it will be something else. Okay? Now, if I take this idea to the plane and I am trying to find out the line, how do I extend that idea? So instead of interval, what should I look at? So I have to look at median of the deviations. So what is the analog of interval in this case? So when I have lines, now, in the plane, so it should be something around the line. So what is the geometric object that I need to look at? It should be a strip, right? It should be a strip. So I will have to look for something like 3 data points. 2 data points will give me a line, and through the third point I will draw a parallel line, and that strip should be chosen in such a way that the vertical width of the strip is smallest. Okay. Now how to choose those 3 points? Those 3 points you choose, and the corresponding line you choose by solving that Chebyshev problem. So you solve a little Chebyshev problem with 3 data points, take the 3 lines and form the strip and do that. Okay. So again, there will be these elemental solutions. For every 3 points, you have a solution to the Chebyshev problem, and one of those solutions is a solution to the least median of deviation problem. Okay. So again, if you have a large data set, the only way you can solve it by using this Markov chain Monte Carlo. Okay. There is no good algorithm if your n is really, really large. Particularly for this one, I mean, for the other one, you had at least a simplex formulation. Here, there is no alternative formulation that is known yet. Okay. So as far as I know, I mean, see, people have tried different algorithms, but when we came to know about simulated annealing and implemented that, that turns out to be the best answer to the question or the best solution to the problem in terms of efficiency, in terms of computing time and such things, and in terms of accuracy also. Because see, all other algorithms that are available for this problem, they are also approximate, and there is no 100% guarantee that it will hit the global minimum. Okay. So one way you compare different algorithms is that you sort of do a huge computation and find out the global minimum. And then you try to compare different algorithms to see that if you run these algorithms for 1 hour or 2 hours, whether it is actually hitting the global minimum or not. Okay. And there, simulated annealing has an edge over most of the other algorithms that are available for this. Okay. So this is more or less what I had prepared. So if you have any question, I will try to answer that now. So these are all combinatorial optimization problems, and simulated annealing is very powerful for such problems when there is no other better algorithm. Okay. So it's like if the problem has no simple structure, that will help you to simplify the problem into some other problem for which you have an elegant solution like the simplex or some such thing. Simulated annealing seems to be the only solution, and that's a very powerful solution.